and welcome to Cherry Pie Math. This video is going to go over single event probabilities. Before we get started, you should know how to format a basic probability. I'll do an example here. What's the probability a random state begins with the first letter as your name? I'm just going to use Cherry. So Cherry starts with a C. There are 3 states that start with C: California, Colorado, and Connecticut. I did look this up right before I made this video. So that would be 3 out of 50. That would be my probability in fraction form. That's as reduced as it can get, as simplified as it gets. Because it's the number of successes. So let me write that number, successes, over the number of possibilities. And remember, successes in probability doesn't mean something good. It means what we're looking for. In this case, it really doesn't, it doesn't mean that a state that starts with C is better than any other state, right? It just means that's what I was looking for. So also in probability, writing that entire sentence, what is the probability of this happening with this and this and this and this, is so annoying. And as someone who's been making some notes and some homework to go along with these videos, I was just kind of frustrated. I was like, I don't really want to keep writing this, but I will for the sake of learning. So finally, we're at this point where we can introduce something called a notation. A notation is like a mathematical way of shorthanding it so that we don't have to keep writing the same thing over and over again. So the notation is capital P, and then in parentheses, we write what we're looking for in our success. That was a terrible way of writing success. Let me try that again. I have this rubber tip on my Apple Pencil because it helps it kind of be quieter when I'm writing on my iPad, but it makes it hard to write it nicely. Anyway, so and I'll do some examples so that makes sense. So we write P, and then in parentheses, we write what we're looking for, essentially. So let's say we're looking for the probability of drawing a club from a deck of cards. You would write P and then club, because we're looking for a club. Or if I was looking for a student whose last name was W, I would say the probability of W. And that's how you would read it. You say the probability of, and then whatever's in the parentheses. And then the probability of getting a green Lego out of a box would be P parentheses green. That means the probability of drawing a green. Notice that if I looked at just P of green, I'd be like, what on earth are you talking about? I do need to have a little bit of context. But the idea is that instead of having to rewrite it every single time, if you have a table or a general case, that this way you can just write P parentheses this, and it obviously references something that you're looking at. So for example, we have this table here. All of these are obviously referencing the table up here. So if I just said P of lefty, actually that's a bad example, P plays sports, or the probability of playing sports, you'd be like, who are we talking about? What are the numbers? But obviously I have this table up in front, and so all of these are obviously referencing that. But I didn't have to rewrite the probability of that someone that you draw randomly plays sports. Instead, I just wrote P parentheses sports, and I was done. So with that out of the way, let's go ahead and calculate these. Remember that probabilities can be fractions, decimals, or percentages. What I have found in my experience is that it's easiest to make the fraction, especially when you're asked to calculate something from a table, but then you have to reduce the fraction, and that's pretty annoying. So I kind of do a mix. I do the fraction first, and then I'm going to convert it to a percentage, because nobody likes decimals. Well, okay, maybe librarians like decimals, but even I teach math, and I don't like decimals. I think they look kind of ugly. Anyway, so the probability of someone is a lefty, that's what this is saying, or basically the probability you pick someone randomly and they are a lefty. That would be 52 total people that are in the left-handed, right? This whole thing represents left-handed people that have been surveyed in this case. So I would have 52 of them were left-handed, and I would have it out of 400 total options. So that's how I formatted it. But like I said, you do have to reduce that fraction, or you can just convert it to a percentage. So in your calculator, you would do 52 divided by 400, and you would have 13%. Ta-da! And that would be your probability there. The probability that they're left-handed and play sports. So that would be, we know we're in the left-handed part, and we know that they're in the play sports part. And because it's and, it means both of them have to be happening at the same time. It has to be a person that exhibits both of those traits. And that would be 29 people out of 400. And again, I'm going to turn to my handy-dandy calculator, do 229 divided by 400, which I get 7.25%. Unfortunately, I do have to include my decimals here. I didn't really have a choice. I'm sorry. Let's say the probability that they play sports is 276 of them play sports out of 400 people. And that's just how we're basically just doing a lot of experimental probabilities here. We have the survey already. We're using the experimental probability now to help us calculate theoretical probability in the future. Probability that they don't play sports, 124 of them didn't play sports out of 400 that were asked, which is 31%. And one thing I want to note here is that they either play sports or they don't play sports. And so the probability that they are in sports or not in sports would be 100%, right? So that is indicative inside the percentages that we got as well. We did do these calculations separately, but you can also look at the percentages here. You could say, oh, there's 100% of people and 69% of them play sports. That means 31 of them don't play sports. So I just think that's kind of cool. I'm going to skip this one for now. I'm going to come back to it in a second. And then right-handed, we have 348 out of 400. I do that in my calculator, and I get 87%, kind of same thing. They're either right or left-handed, and so that adds up to 100%. Let's go back to the right or not play sports. We know that all of these people, this whole row represents right-handedness, and we know that this whole row represents does not play sports. We are not looking for just the people who are right-handed and don't play sports. They are in there. But it's saying they are right-handed or they don't play sports. It could be either or it could be both, right? We're not going to exclude the overlap of people. It's saying as long as they fit into one of these categories, that's someone that we're looking at. There are two ways to do it that I've seen. Some students will do this plus this plus this, and other students will do this plus this, but you have to be careful when you do that. If you add 124 plus 348, you're going to get something larger than 400. But you cannot have larger than 400 because we were only asking 400 people. The issue with that is when you add these together, you are double counting that 101. So you can do this. You can do 124 plus 348 as long as you remember to subtract 101 because you double counted it. So I'm just going to do 247 plus 101 plus 23. So 247 plus 101 plus 23, which is 371. I'm going to divide that by 400, and I get 92.75%. So, just something to remember. And this is tricky, the and versus the or. The best thing I can tell you is that and is where they cross over each other. So play sports and left-handed cross right here. And then or is everybody that you're highlighting. So this whole row and that whole column, just be careful about double counting. One thing to note of that entire survey is that example showed where every single person was random. So when we were calculating these probabilities, we were saying, what's the probability that a random person that I select will have these qualities? Every person had the same likelihood of being selected. It was just 1 out of 400. They were just one individual out of 400 total people. So that's what that means. It means that every single person had the same chance or probability of being selected. So let's think of some examples where every single option has the same likelihood of being selected. Maybe like drawing from a deck of cards. Every card has the same probability. Or flipping a coin. Just think of some things like what is something where every single option has the same probability of being selected. And that's kind of like, I'm going to call it equal randomness. Everything has the same probability of being selected. But then we also have non-equal randomness. Let's think about sports. I know that we've been watching football lately, and some teams are better than other teams. And so when you go into a game, you don't go in thinking, oh, there's a 50-50 chance between these teams. You go in thinking, oh, I think this team is better. They have a higher percentage of a higher probability of winning. Because let's think about a basketball player. Let's say a basketball player has 89% free throw percentage, but there's only two outcomes. They can either make it or they don't make it. So is it the same likelihood that they make the free throw and they don't make the free throw? No, we know that there's an 89% chance that they do make the free throw. This is not equal randomness. It is not an equal probability of making the free throw versus not making the free throw. So some other examples is especially in sports, like sports betting. That's why betting is really dangerous. And I'm just going to say that, like, I do not recommend betting because any given Sunday, right? What's another option? Maybe like, have you ever thrown a water bottle and tried to get it like to land on, the bottom of the water bottle? I know that's a lot of fun. Please don't do that to your teachers. I had one explode and I was not very happy about it. But those are examples of things that are not necessarily random, right? Because when you throw it, it's not the same percentage, it's not the same probability of each of the outcomes. So I'm not going to do this here, but I want you to pause the video and try it. I want you to grab a big-ish coin, flip it 10 times, trying to get heads. So just write, like, did you get heads, did you get tails? But then put something, and then find the theoretical probability and the experimental probability with those. But then using that same coin, try to put like weight on one side of them. And that's why, like, when you go to Vegas, it's such a big deal that you have to have like brand new everything, because people try to trick the system, right? They try to get like those weighted dice or whatever. So I want you to put something heavy on one side, maybe like you have a little bit of duct tape or something, and throw that and see what happens to the coin. Does it change your percentage at all? And what does it change your theoretical and experimental probability? So try that. Think about what happened. I'm going to go back here, pause it. Okay, maybe you didn't pause it, but you can probably guess that when you did that experiment, when you added something heavy to one side of the coin, it was no longer a 50-50 chance. It did change the percentage of what happens to your coin. So some things to remember. One of the biggest things, remember that P and then parentheses success is just a notation for how we write probability. Remember not to double count when you have an or. Remember that, like, in the chart we had to subtract the 101 because we counted it twice. And then finally, remember that not all probability is random, and actually most of the time it's not. You have a percentage of something happening versus something not happening. Anyway, I hope that helps, and good luck.